one more talk, right, and
Just,
then
yeah.
and then two proposals. So Sachi Surampur is double task.
Okay, everybody in your seats. Now.
Before we flash up the numbers,
The only thing between lunch and you is me.
that's not true.
Okay, so we've been here all morning, and I'm sure you're all asking, are we there yet?
Lunch? No.
Well, we're almost there. Just a little more patience. So we're about here, and we need to get here. So just a little bit more. Just before I go on, the red and the, I don't know, orange names, these are the students, and I just wanted everybody to see that this is a student-heavy team. They've done a lot of the heavy lifting, and so I'll say a little bit more about that as I go along.
And the colors mean?
The red means the undergraduates, the really hard workers, and the brown means the less hard workers, and the black means they don't work at all. Okay, the results so far, right? You've seen lots and lots of results. We've tried many interesting feature functions, many interesting ways to test the grammaticality of the MP output and see if we can improve it. And I said more than 440 individual features because even as of yesterday afternoon, new feature functions were being added and tried out and so on. And I think the current number is 455 or something, and we'll keep growing until we unplug the machines or something. And the nice thing is that we try each of these functions individually by training them on this dev test, which is the 2001 list eval, and then we actually test it out. And when we do that, we actually combine it with a good system so that it's being tested honestly and not on its own under some deprived or deficient system. And this has been a pretty good setup. It's arguably quite adequate for trying out these individual features, and you've seen many of them. But I'm going to say something stronger about this methodology because the people who developed it are too modest. This thing has really allowed us to do a lot of rapid experimentation. And you can imagine it allowed many of us to work in parallel, try new things, and also put them all back together in a very good system. And I remember, maybe my impression is faulty, but I remember one afternoon, Franz and I were in a steering committee meeting, and the grad student Shankar and Alex were trying to get all the parsers done so that we could do something about it. And the undergrads were trying interesting feature functions to see and improve the NP system. So this tells you what this thing does for you, that you can bring somebody in who hasn't worked in this field before, give them a few tools, and poof, they start producing interesting results. So this has been a big help. For those who like numbers.
Do you have some plan for some SETI-like architecture here? We'll get the whole country making these feature functions.
Hey, Franz, maybe that should be a proposal. Yes.
You want to get a proposal in our session?
All right. Yeah. So for those who like numbers, I can give you lots and lots and lots of numbers. But before I show any numbers, the baseline is 31.6%. So I'm not going to show it to you. It's there. And so in the morning, we heard from first David Smith about what we call implicit syntax, which is a polite way of saying not syntax. And there are all these features we tried. And these are very cryptic names, but this is again to emphasize what we're really doing in the summer. All we did is we said, okay, you want to assign a Model 1 score to a Chinese sentence and its hypothesized translation? Okay, give it a number. If you give me 1,000 numbers for every Chinese sentence in the dev data, I can train. If you give me another 1,000 numbers on every hypothesis in the test data, I'll give you a blue score. So that's why all these are just feature function names, Model 1 features. David talked about missing function words, important words which don't show up, or Drago's popularity numbers. These are all the features, these are the blue scores. After that, Alex and Jen talked about shallow syntax, the kind of stuff you can get your hands on easily, parse speech, NP chunks, and so on. And many different things were tried with that. And Alex talked in particular about the projected tag language model, and somewhere in here there are things like the sequence of NP, the sequence of chunks, whether they go well with each other or not, and so on and so forth. After that, those who really love numbers, there are even more of them. We had deep syntax, which means, by the way, deep syntax here just meant you actually use the trees as opposed to ignoring the trees and using the chunks. It's not the linguistic notion of going beyond just the constituents and trying to do something deep with it. So Kenji and Catherine talked about this. Again, we tried lots of interesting features. There is your tree to string alignment score. There is your dependency language model. And then these are things like how many does the main verb on the Chinese side align with the main verb in the English side? Here is your parser probability. What is the Collins parser assigned to this sentence and its parse tree and so on and so forth. And of course, while we were doing this, we realized that a lot of this direct tree-to-tree alignment, trying to figure out which part of this tree goes with which part of that tree, is kind of a lot of work, both computationally and modeling-wise. So we developed the so-called machete principle, which falls under our category of tricky syntax, which means we said once you have the two trees and the two word strings, there is already a word-to-word alignment provided by our MT system. Try and use that to simplify the tree-to-tree alignment. And that's essentially what this tricky syntax is all about. It tries to use the word alignments to simplify the tree-to-tree alignments and work with them. And there again, we tried lots of features. I don't even know how to pronounce some of these words. Maybe they're not meant to be pronounced. And you have their scores. And so these are all the things we tried. Right? And so it was really great, and we had all these ideas. And now comes integration. We put them all together, and all these little things, how do we do it? So we took essentially a greedy approach. We said, take the best system that we have right now. Amongst all these features that we have, choose the one that improves the blue score the most. Throw it in and sort of recreate a new baseline system. Hopefully this will be a little bit better than the previous one. And then do it again. Look at all the remaining features, see which one of them improves most over this baseline. And to give you some perspective what this is, like, maybe you should go back to the middle of 2001 and say, you have the Cherniak parser, which is, according to Eugene himself, the best English parser on the planet at the time, and try and improve it. And so that's what we're doing. This is the best system. And we went on iterating. But this is all like, in the realm, this is along the lines of trying to improve the model, train the model discriminatively so that it gives you, it prefers good hypotheses over bad ones. But there's not.
I said the universe.
The universe. Yeah, that's true. I mean, what are the odds some other planet speaks English, right?
We have to consult Celia.
Okay, but then remember, there is one more thing. Shankar talked about the scoring criterion. You could always choose a hypothesis, not the one that is most likely under this model, but in fact, the one that minimizes whatever criterion you want to minimize. So we could always do that on top of anything else we've done. And in 2 or 3 cases that he looked at, you get a good solid 0.3% on top of whatever your best system is. So I won't talk so much about this right now. I'll just tell you what we did up here. We did this. So we had a baseline system which has no new features in it. So what's on this axis is the blue score going from 30.5 up to 33.5. On this axis, we're adding new features, 1 new feature, 2, 3, 4, 5, and so on. So before we add anything, our test performance, blue line is test set, red line is the dev set, so we're sort of tuning on this, testing on that. So this is the 31.6% baseline, right? So as we add more and more features, sure enough, the performance on the training set keeps going up. The performance in the test set goes up a bit, then starts wiggling around, and we went, I think, up to 30, 40, 50 or something, and it's sort of over here.
So you're going to comment more on this interesting curve, right?
Just a little more.
Because it looks like, I mean, does it matter what feature you add, or does it always
Oh,
go
yeah.
from
It's
31.6 up and then stop
Oh,
on the
no.
test set?
Oh, on the test set. Well,
Yeah.
this is actually a curve for one particular run of this greedy approach. We didn't try, like, okay, leave the first guy out, let somebody else speak first. We didn't do. Is that what you're thinking? No.
It's just as on the surface, it looks like, the first feature gets you everything and nothing else matters. On the test set. On the test set, and then the rest is all overtraining. You're just adding a bunch of.
Yeah, probably.
That's
probably. This is for the question answer and discussion.
Okay.
What's the first guy, by the way?
Sorry?
What's the first guy?
Don't you want to know all of them?
I mean, what's the first guy?
It doesn't
first
matter.
step?
That's the point you just made.
No, hold on. It does matter. So here are the features. So what are these 12 features that you saw over there, right? Well, the first one is model 1 probability. And no, this is important. What it's saying is go back to basics. It's saying that when you're trying to do this translation, remember, what is model 1? It says take the English sentence, treat it as a bag of words, take the Chinese sentence, treat that as a bag of words, and ask yourself, how similar are these two bags of words? Bag of words remind you of IR topics. So this is like saying, pay attention to the overall coherence of the sentence. If you're choosing content words, choose things that hang out together. So, second feature, it was nice to see that some of our contrastive error analysis was good. The feature is a binary feature. If a verb heads the English sentence, it's a 1. If the verb doesn't head the English sentence, it's a 0. And the feature says it's good if it's true most of the time, that English sentences are headed by words. Other features, the number of singular nouns. This might be peculiar to Chinese because there are no plurals, and so our system constantly produces singular nouns. And we seem to have discovered that it's good to have a few plural nouns in an English sentence. So, fixed points. So what happens is that when you translate significant achievements, remarkable achievements, fantastic achievements, achievement seems to be sort of a fixed point in all these translations. So we looked at the reference translations on the dev data, found these words which tend to be fixed points, and sure, the more of them you see in the output of the test data, the better it is. Number of possessives. So this was, I don't know if you remember Catherine's example, in one dependency there was China cities, and the other dependency was China apostrophe S cities. So if you have a possessive, take it. It's probably a good thing.
I'm just curious, if you actually did this on all of the full training data,
Right.
how long would it take computation?
I
I mean, right now you're training on this dev set, which has a total of 900 sentences
Right.
in it. What if you did it on the whole mess? How long? You know?
Well, we have to sort of make our baseline system a little deficient, right? Because we've used up all the other parallel data for.
I'm just trying to get a rough feeling for the computation. That's
So
all.
right now we use 1,000 sentences for training, and instead, so there's 25,000 words. Instead would be 150 million words, so basically that fraction which is 300 times lower, the training part of it. But obviously you would have to generate path trees and all that stuff for the data, so it would be enormously more time consuming.
So 1,000 hypotheses for each sentence, 2 parse trees for each hypothesis.
So depending upon what feature you're adding, some of them are grossly computationally slow and some are sort of trivial, like
Right.
the Model 1 problem.
One
Right.
no problem.
Yeah.
Right.
Yep.
In a typical decoding scenario, you don't have any reference translations first place. I'm talking about the fixed points feature.
Oh, okay. No,
and
we-
in a typical training scenario, you only have one translation.
Right. So the fixed point feature, in this case, we actually picked them up from the 993 dev and tested them out. You're right, in a more natural
Realistic sense,
setting.
you know,
Yeah,
this
well,
scenario.
it was there. You asked which feature was there in that case. Okay. Again, this is some other odd stuff coming out. If you see verbs which are not present tense verbs which are not third person singular, it's a good thing. Don't ask me why. This is one of the more interesting syntactic features. So if you have two noun phrases aligned, you look at the trees above them. So if the in Chinese noun phrase is kind of flat and the English noun phrase has a lot of nesting, it's not a good thing. And say the other way around too. If the Chinese noun phrase is very hierarchical and the English noun phrase is flat, we don't like it, or rather, moderners don't like it. Matching constituents around coordinating conjunctions. If you see big dog and something something, it better be adjective noun, and the more of that you see, the better, and the less of it you see, you get a lower score. Number of content words that go untranslated. So content word simply means if you didn't occur often enough, you're a content word, and so on and so forth. So I could just go on with these features, but here's the more important thing. Actually, maybe I should go back here. This improvement is 1.6%. In the beginning of the workshop, we thought we were going to get a big improvement, and of course, we had hundreds of these features which have small improvements, but they're not adding up. Oops. Let's see. Okay. So we think that there's probably a problem with this way of the log linear combination with this maximum blue. Maybe we need something more sophisticated because these features are fairly complementary, and we think that they will improve. So for example, number of matching constituents.
Are they really fairly complementary? You have your baseline system is a phrase-based system, and you have long phrases that capture local syntax and local word order already.
Right.
And your top end list doesn't have much reordering anyway. So I'm not sure if taking
So what I'm saying is, for example, the things like if you're comparing lexical dependencies, and if you're comparing, for example, the matching parentheses. like, those two have pretty much nothing to do with each
No,
other.
these features are complementary among the features themselves, but
Right.
they're not great on top of the prior model that is already strong in terms of what you want to capture.
Yeah, but each of them gave a small improvement on the prior model, so when you add them, why aren't they adding up? That's the question. So each of them does give a small improvement on top of the baseline. I need to hurry up a little because this is sort of short.
Actually, you need to hurry up a lot.
So this is my last comment, right? Okay. So the other thing is that several people remarked on it. If you remember Shankar's minimum risk rescoring, if he tries to optimize for the parse kernel, which basically tries to make these trees more analyzable and well structured, the blue score drops. And we found that, for example, very often things which we think are clearly making the output more readable are not being picked up by this maximum blue training. So perhaps we need to look into what one should train for. And one of the more interesting things was that people said, if a machine translation system has 80% of human blue score, then that's not a big deal, just try a higher N for blue. We in fact tried it, and in fact if you look at 9-gram overlaps, even then our Oracle best is 106% of human performance, or just 105. And clearly if I gave you 5 examples of Oracle versus human, in each case you would pick out which one was the machine produced output and which one was the human, except for a couple of humans.
You have a lousy human in your average.
Maybe. But in any case, so the point is that there's clearly, and we had this discussion earlier, there's clearly a lot to be done about what to tune these systems for, and in fact that's exactly what we're going to have to propose with them. So, Viren, okay. Any questions from you while Viren switches over?
We need to end at 1 o'clock, and so they will get 10 minutes, and then we'll have, if everything goes well, we'll have 10 minutes for a general discussion.
Okay.
But I'd like to enforce the time on this thing.
We'll start later. Go ahead.
So I'm one of the undergrads on the syntax team, and I'll be talking about a proposal based on MT evaluation. So there's lots of things to say about MT evaluation, but one of maybe the less controversial things is that it's been useful to the machine translation community in the past few years. It's important to have automated methods of evaluating translations that are both objective and cheap to get, because human evaluations are expensive and slow, and so a workshop like this would be completely impossible without automated means of evaluating the results. Scores like blue and NIS, which are basically based on n-gram precision, there's lots of things to say about them too, but in the past few years they have at least been useful to the extent that humans do prefer state-of-the-art translations, and so do blue scores. So at least for the past few years they have been useful. But we're beginning to see some problems, and maybe we run into those problems in these workshops. We can create feature functions all day, but if our blue and NIS scores don't reflect these changes and don't reflect accurate measures of fluency, then we can't really tell what we're doing, how well we're doing. So just to point out some of the recent evidence for issues with blue and NIS scores. So as you just pointed out, for example, our Oracle best sentence achieves 105% of humans, and recent time evaluation, which is a bit more systematic, that achieves 89% of human quality. And it's easy to tell that these systems are not really close to humans, and certainly not above human quality, just by looking at them. And the conclusion there may be that current metrics of n-gram precision are just not good enough to distinguish between current MT output from a phrase translation system and clearly superior human translations. So a proposal for the research project is to explore new metrics for MT evaluation. Specifically, what we'd like to do is to collect all available MT evaluation results which have human judgments attached to them. So things like the TIES evals, older RSL, and the Rumogo project in Germany at the University of Aachen has some evaluation data that has human metrics, human evaluations of translations. And we'd like to explore new measures that correlate highly with these human judgments. And then investigate methods of combining different metrics into a single score that overall has robust correlation with human judgments. So one of the ideas we'd like to look at is consensus-based lexical evaluation. So the idea is that current n-gram precision scores don't weight lexical sequences that appear in multiple references more heavily than others. And the intuitive reason why you want to do this is that important words like proper nouns and key phrases would be likely to appear in multiple reference translations. And so we'd also like those to appear in our MT output. And so we'd like to weight those more heavily than maybe some other words. And the idea here is not to promote fluency necessarily, but to promote lexical content that accurately reflects the source data. And additional features that we'd exploit for evaluation metrics are syntax-based fluency judgments. So we explored a variety of different syntax-based techniques for evaluating sentences this summer. We'd like to exploit some of them and see whether we can extract measures that correlate with human judgments. And one might argue that our results from the workshop are somewhat ambiguous. It's hard to distinguish between bad sentences. Well, this is exactly the point. Maybe the blue measure just isn't telling us what we're doing. So if we can find syntax-based measures that correlate with human judgments, then maybe we can sort out the issues more specifically. And so the idea here is to reward fluency of sentences. And the general methodology which we'd like to employ is to investigate, collect all the data that has human judgments, investigate the new metrics, see whether they correlate with human judgments, and then see whether we can train statistical models that combine these different metrics into one score, which overall is robust to human judgment. And really, we'd also like to emphasize that one part of this project would be to use these scores to regenerate, to re-rank MT output. So Franzak's system, which we used during the workshop, directly optimizes your loss, your error criterion. So in this case, we were using blue during the summer. But we'd like to see if whether using new evaluation scores will produce more favorable output, which can be evaluated on an initially anecdotal basis, obviously by humans. But if it seems promising, then maybe more systematic evaluation would be used. That's it. And now we'll do some.
There might be some question.
Yeah. I was just wondering, do you have, I haven't actually looked through the proposal itself, but do you have more specific things you're proposing in terms of detailed metrics you're going to try?
Yeah, so the consensus-based stuff, that's in itself fairly specific. I mean, that's basically just a reweighting of what something like blue is doing. As far as the syntax-based stuff goes, some of the more shallow syntactic features that we looked at during the summer, like part speech or trunk-level information, and comparing candidate translations with references, based on those, we'll be interested to see whether we can find loss functions there that correlate with human judgments between translations.
And just to put this in context, I'm no machine translation expert, so forgive the ignorance of the question, but I somehow got the impression that a lot of people have tried a lot of, coming up with a lot of metrics for machine translation, and the reason where people are using blue is it's actually after people having tried lots and lots and lots of things, this is one of the few things that people have come up with that actually have some vague correlation with human performance in the first place. So I'm just wondering what new, what will you be doing? It's not clear what's going to be, what you're doing fits in with the past history of lots and lots of machine translation metrics and why it would actually be an improvement over blue.
Well, one thing is that I'm not aware of anybody, I might be wrong, but systematically collecting all data that's out there that contains human judgments and then comparing various measures and their correlations to that. And the other part that would be relevant to the question is, I suppose, the syntax-based stuff, exploiting techniques that we developed during this workshop and seeing whether we can find correlations there. And there has been work before in this, and it's obviously a study problem, but it doesn't, it would seem quick to say that the problem is not solvable beyond current means like blue, because clearly there are problems with blue, and there are advantages to blue, clearly, It does tell us something, but maybe not enough, and could be further worked on.
Is there some problem that you could run into if the features you use for evaluation are matched to the features that you use for translation, so that you get into a sort of incestuous relationship?
Right.
I remember a zillion years ago, people used to build things to rank vocoders, use the same filter banks that were in the vocoders themselves and the same energy measures.
Right, so the idea would be to test the end-to-end performance, not via the metric itself, which would basically be meaningless, but by humans. So just going through and looking at the sentences and seeing what kind of difference there are. And if there are improvements on just an anecdotal level, maybe taking a more systematic look at it. But all the while comparing these measures on an individual basis against our collective human judgment data.
But if you, suppose you discover that X, Y, and Z in some syntax-based method actually correlate really well. Isn't it a foregone conclusion that your new best system is going to be the old system plus X, Y, and Z?
Right, but if our metrics don't capture that improvement via X, Y, and Z, then
Well, but X, Y, and Z are things that you can automatically collect, and thus can be made into features, and thus can be put into your MT system.
Well, for the MT
No,
evaluation,
no,
the task is much simpler. MT evaluation, we have references. So for the features we have for the MT system, we only can rely on the Chinese input sentence and the baseline suggested translations. So MT evaluation can exploit a lot of different features by looking at the references. So I think that's a big difference there. You cannot easily, things which work for a machine translation evaluation, you cannot directly plug into a machine translation system. You can do them with maximum training with respect to that, but you cannot directly take into account the features in the same way. Because you don't have
best lists? If you had n best lists?
True, but you don't have the reference. The best lists are bad translations. And for MT evaluation, you have the references which provide the relevant information why evaluation is much easier than translation itself.
I'd like to end debate. If you have a very one
I have a very
sentence.
quick comment. One example of something that we want the system to have is what are the fixed points in the multiple translations, the reference translations. So the MT system has no answer.
Right.
Okay, thank you.
The topic of our proposal is discriminative re-ranking for machine translation. And what we have done here is that we have designed and implemented a multi-bias perception algorithm for machine re-ranking, and we have used it to set up two kinds of experiments, and we use 30 comprehensive features, and we get some risk of 31 concepts, and we also try to use fragments of syntactic structured features. And although the data set is small, we also get promising results. So we have learned two things. First, it's not easy to apply discriminative machine learning. And our algorithm didn't work well in our current data set. And then secondly is that maybe it's worthwhile to have a try because the results by using fragments of syntactic structure is promising. And one thing we are sure is that the best way to use discriminative learning is to use the re-ranking techniques. And the idea is that first, the baseline machine translation generates n-best translations, and we extract features from each candidate's translation. Then we re-rank these n-best lists by discriminative learning. And the goodness of this approach is that we can search for global optimum if the test n-best list is good enough. And the secondly is that we can use features in available generative models that generate. And we can also use features of various kinds at the same time. And in past re-ranking tasks, various re-ranking algorithms have been successfully used, such as variants of boosting, perception, SVMs, as well as the block-learning model. The nature idea is that the way that we can do the same thing, we just apply this algorithm to machine translation, but this is not the easy way. First, for machine translation, we don't have those and we have multi-reference. So the result is that we cannot say one, for example, for two translation, one get a score of 6, another get a score of 6.2. It's hard to say one is better than the other. We don't have reliable score for single translations. So we needed to find a way to adapt those machine learning algorithm to machine translation, and the multi-bias perception is our first try in this approach. And what's the difference between our proposal with MTV replicating useful workshop is two aspects. First, we define the training data set. In the workshop, we have a small training set and a huge MS list. And obviously, this is not good for discriminant learning. We use a large training set, but with a short MS list. And in between, we can use individual structured features. And since the training data is different, and obviously the learning structure is different. And for the data set using workshop regression or gradient methods are better methods to do re-ranking. And in our new data set, and obviously the discriminant is better. And we think that descriptive learning is more suitable for machine translation for the reason that we lack of the reliable measures of the quality of single translation. And if we use this unreliable score in the training, maybe not a good idea. But something we show that, for example, this translation is better than such translation. We are sure of that, and we use all this kind of stuff in the training set. Maybe it's a good idea. And our proposal is that first we want to build a training data set of 100,000 training sentences. For each one, we select 10 good translations, 10 bad translations from 1,000 best list. And for the baseline machine translation, we would like it to use only simple language model and alignment model with simple principle, like the baseline machine translation system we have used in the workshop. And the MT system also provides the word-to-word alignments for each candidate. And then we extract the rich feature structures from those candidates. We do tagging, parsing, and we can get alignments on complex structure automatically. And the features we would like to use are two kinds. One is to use features to handle language models like chunking environment, Apache, LTAG, and things like that. And another class of the will be modules for vSync. And those are two of the candidates that we have used in our in the Sangha, and like a line dependent structure and a pairwise line pixel, LTAG parameter tree. But the difference is that we use each individual structure as a feature instead of compute a score on that.
As far as the proposal is concerned, I'm a little hazy on. Are you proposing to not only try the discriminative training approach on more data, and also to invent another 450 features, or are you going to basically take the features you developed at the workshop and toss them in, but train it on a lot more data?
Firstly, I would say the feature we would use in the discriminant model is different with the feature we have here. Here we use so-called comprehensive features. For example, we need to build a language model to get a value of a feature. But what we propose to do is to use individual structure, each individual structure as a feature. You will see that the feature space will be very large, like 100,000. We use individual structure as features. And we can design features similar to what we have done, but we use a different, we use single structures as features. And the advantage of this approach is that first we can use an arbitrary fragment of syntactic structure as features, and since we use each individual one as a feature, and those features take the directory if they are good, and the goodness is that smoothing is resolved automatically. We don't need to worry about the back-off model, And it's easy to test the potential features because we don't need to build a language model to compute values like that. And in this way, we also avoid decoding on complex features because it will achieve automatically. And the last is that this method is theoretically well-founded and has been shown effective in passing. That's it.
Given that there seems to be some computational issues here, do you have the computational resources you need, or would you be using, Hopkins or what to run some of this stuff off? Or is that part of the proposal to ask for a bunch of computers?
Yeah, the computational results is a problem. So this way we say 100,000 sentences instead of 1 million sentences. This is kind of consideration. And actually we were started from we first started with a small data set with 10,000 Chinese sentences and build a toy system to see whether this approach works or not. And to estimate the final cost of this approach. And definitely I think this approach should be efficient than the traditional machine translation system since to build a ranking system is easier kind of thing.
No other question. Franz will conclude and then hopefully we'll have some time for overall discussion.
Perhaps you could tell the judges that the students will be available tomorrow in case.
I told them.
Yes. So tell us again.
No, he told you.
Okay, so we arrived now at the conclusions. I will very quickly go through and very quickly summarize what we did. So we started with the best existing Chinese statistical machine translation system as baseline. So we had a very strong baseline there, and therefore it's obviously very hard to get them over the best existing system. And the goal was to improve the syntactic well-formed-ness of the output by re-ranking of invest lists. We developed 450 different feature functions in these different categories. The improvements we got were relatively high for some of the implicit feature functions. Unfortunately, Model 1 gave the largest improvement, which cannot be given a very specific syntactic interpretation. So we call it semantics. So we even got beyond our original goals to only work on syntax, but even work on semantics. And so shallow and tricky give also some improvements, and the improvements for deep are even smaller. So at least for looking at the single features and average. This is the typical behavior of these feature functions. But end to end, we achieved then a nice improvement. So from 31.6 to 33.2%, where the largest improvement actually comes from Model 1 and from minimum base risk. And then some of the other feature functions help also to improve, to yield that score. But obviously we would have liked even larger improvement. But who was here in the initial presentation, I gave different categories for different kinds of improvements. And so that was in the category okay. So it's significantly better than the original, and it's almost good according to the original classification of these improvements. So, but a very important resource, or very important achievement in this workshop also has been the creative resources. So we have these invested 16,384 best translations for even larger sets. We only work on these 900 development sentences and 878 test sentences. But we have computed it for a much larger set, and even have a blind test corpus held out for future experiments, which we didn't touch so far. And so these can be used for a lot of different experiments, not only for syntactic feature functions, but also machine learning, language model rescoring. And hopefully anybody will then be able to use that. And so we have these passes for the first 1,000 sentences, which is a huge computing time was necessary in order to get that, so that's a very valuable resource. With these part of speech tags, chunk passes, not only for the invest translation, but also for the large part of the training sentences. So 1.3 million English sentences are passed, 50,000 Chinese sentences. We have these feature function files, which directly, so if somebody wants to make machine learning and get develop better methods to exploit And it's useful for language modeling research, machine learning research, and for that kind of research that we actually did. Very quickly to lessons learned. So one of the lessons learned, I have the feeling that we have to really experience the limits and weaknesses of the bleu score, and especially also this training method that has been used, the maximum bleu training. And it seems that we need better automatic sentence level metrics. At one hand, because we want to make this contrastive error analysis. We want to analyze in sentence per sentence level what goes wrong, and we want a metric that shows us the sentences which are very bad and the sentences which are better. And we want to use this in order to optimize, to tune our system. And right now, if we look at these sentences, and especially also looking at this result of the Blues, or Oracle has 105% of human performance, and still it's very bad. So I think it's possible to improve that, and so there has been this research proposal by Björn. Another problem is that the maximum bleu training does not scale up to hundreds of features of the specific training techniques. And so there are needed refined discriminative training techniques that now can take into account all these 400 features and try to add up all these excellent improvements to a significant improvement. So there is a research proposal by Libby. And another lesson learned, these off-the-shelf parsers to use for noisy MT output is, let's say, problematic. Disagreement, but...
well, I mean, you know, Collins' parser isn't robust. You shouldn't use mine.
Well, we will do that next time. We actually had to parse a lot of sentences also with your parser. But the point is not that some sentences fail to parse. The point is more that the parsers which are produced, they are basically hallucinated structures in there. Very many sentences in best lists simply have no structure. And so the parser gives a structure, finds a verb phrase, and so on. So our feature function, which is want to look at the fact that there is no verb phrase in the sentence, because humans look there and they don't find a verb phrase, and the parser says there is one. So this kind of things we talk here. Not so much that the 3% has not been passed. It also caused some problems, but it's more technical nature. So ideally, you would have
hallucination is a much more serious problem.
Yeah. So we would like to have more robust parsers.
They're very robust. They hallucinate all the time. What else can you do with that garbage?
More robust refers to the
honest parser that can call garbage out.
Garbage in, garbage out.
I think we can do that.
Okay, great. And syntactic analysis tools that indicate confidence in the analysis. So the parser sometimes, if he is not sure, he could tell us and could say, okay, there might be a verb there, but I'm not sure. But for those relationships where the parser is sure, it would be great if we have some kind of confidence. And then for these invest lists, there would have to be a low confidence, and we are sure we wouldn't take into account then all these constraints. And the research area, very interesting, I think, is bilingual syntactic analysis. That the parsers on the Chinese side inform the English parsers for the training data already to get better parser performance, and to get this kind of analysis that is bilingual and informs each other. So another very interesting thing that this work environment, I think, actually worked very well. So this combining different feature functions, working on these investors, it's a very nice work environment to allow different people to work independently on the same system, and then that all the results can be combined into one large system. And working on these investors allows us to very easily exploit a lot of arbitrary dependencies. We don't have to work hard in order to get this into a left-to-right search architecture. So you can find which dependencies are important and help us to get better results. And we could later on also implement these dependencies in a different kind of model. That's it.
So we're going to have a general discussion, but I'd like to ask a question first. If you take the original best sentence, achieving, what was it, 31.6 or whatever, and you take the best sentence with 33 point whatever, can you tell the difference?
So we plan to
as
do,
a human being?
We didn't do that systematically. We looked anecdotally, and it seems to get better. But we plan to do a subjective evaluation actually then at this company, some company which does systematic evaluations for Microsoft, and then to give them these sentences, and then they go over it and make these binary judgments. Does it get better or not?
Presumably blind, not telling which one is better.
Right, right. So
Randomized.
randomized, and they don't see it with different judges, 5 different judges, and then we will have hopefully numbers which also show that humans like this more.
So I open the debate for 8 minutes of discussion.
Is it mainly due to computational limits that you didn't try global scale search for the computational features? Or what would you say?
Well,
Can if you have some like better way than greedy methods?
we had this training technique used from the beginning for the baseline system. It proved to be a very successful training technique that allowed to make a lot of improvements over the last time. So here now, but the baseline system had a small number of features. Here now we have this huge number of features, 450 of them, and many of them probably are only noise, but other of them are really information. So the 100 informative features would be now too much for the system to handle, and also has to handle the 300 features which probably don't add anything, and this training technique doesn't scale up to that. I actually tried also in addition maximum entropy training for this, which then would allow to combine all these features. But the experiments there were very inconclusive, so I didn't want to show them. But yeah, we would need other training techniques to do that. And we tried the perceptual learning also, and but there is more research needed in that area.
So is it fair to say that the results showed are already at a peak, or there could be like even better performance?
Well, my expectation is if we had a better learning technique and use exactly these 450 features and just use better machine learning, we get better results. So there's, for example, we did once an experiment where we used these features, that's obviously then somewhat problematic, but we used these features and tested them on the test corpus. And there the possible gain is quite large. So it's unclear then how much that is overfitting to the test corpus or not, but the potential gain there, it goes up to 34.5% or so. So there is still a lot of room for improvement, and my expectation is that better learning will get at least halfway through that improvement. But well, we have to await these better techniques in order to know.
Just along the same lines, how limited do you think you are in drawing conclusions because of the small size of the development training set? I mean, it seems very small, right?
Right. So yeah, sure. We would like. We originally planned then to do the 5,000 sentences of development data, but there the computational problems. An experiment right now takes 2 or 3 hours, and with that it takes 5 times, 6 times as long. But right, so it would be better to try that out after the workshop now on larger corpora to see then if we can avoid some of these overfitting
But
problems.
regarding future workshops that may take similar types of approaches like this, is this just boiled down to then an issue? You know, in speech recognition, the problem we have sometimes right now is it's not even clear we're computation limited. We're still, in many ways, idea limited in terms of coming up with things and then processing. Here, it seems like if you were able to process all of this wonderful data quickly, you might get a lot more useful answers, in which case, you know, it seems there should be some focus somewhere in the community providing like these giant computation servers that people can try out ideas like this for translation alone.
So I think translation in the future will get like speech recognition, where the battle is basically you have to have more machines in order to make more of these kind of applying these learning techniques, and you have to have huge computing power in the background in order to get very good results. So I think that will be very important, and to scale that up. Right now we used only 1,000 sentences. Our full training for this, our full training data is a few million sentences, and using these techniques, re-ranking techniques, right now we cannot handle the large amount of data, but obviously the gains larger using large.
Yeah.
Something like that. Right.
Right.
So it's a fun
Any other?
I just want to comment on that. I think that represented by data, right? So is on the sentence level is already not going to be very good, and we need 4 reference translations for the data, and that's not cheap to produce. It's not like the community is going to come out and give us 1 million sentences with 4 reference translations each. That's not going to happen. So I think that's the other issue.
So I want to ask, did you calculate how many percent for the syntax structure will capture in the human translation from the source to target? So given the syntax structure of the source sentence and also the human translation, did you calculate how many percent of the syntax structure will capture in the human translation?
We computed numbers like this.
Well, I mean, there's the prior work at Maryland, which seemed to estimate that something like 85% of dependency is mapped from Chinese to English in human translations. And, well, parsing work. No. It's the only number I've hit of mine. Heidi Fox does some work in that.
One last question. No last question. Thank you very much. We review